Hey, greetings, Global Impact students. This is Mr. Ellinger. This lesson is on linear programming, and our learning target for the lesson is we want to be able to solve problems using linear programming. Some essential understanding for you for the lesson. Some real-world problems involve multiple linear relationships. Linear programming accounts for all of these linear relationships and gives a solution to the overall problem. The feasible region contains all the points that satisfy all the constraints. Some background knowledge for the lesson. This lesson extends your ability to solve systems of linear inequalities and introduces you to optimization, finding the maximum or minimum value of a function. An objective function is used in linear programming to model some quantity that we wish to maximize or minimize. An objective function may be used to maximize quantities such as profit or items produced, or to minimize quantities such as cost or time. While objective functions in the lesson would not generally have a maximum or minimum value, they may when the region given by the inequalities restricts the domain. An example of a restriction on a domain is as follows. If one variable represented a number of people, that variable could not be negative. So basically, anytime we're solving a real world type of problem, most of the time we're going to be working in the first quadrant where we have positive values. And we're going to use our graphing skills to solve these problems. So let's take a look at how we do this, or what linear programming is. So some real-world problems involve multiple linear relationships. Linear programming accounts for all of these linear relationships and gives the solutions to the problem. The constraints in a linear programming situation form a system of inequalities, like the one at the right. The graph of the system is what's called the feasible region. It contains all points that satisfy all the constraints. So the constraints are these inequalities here. So when we have a system of inequalities, those are called constraints. They're like restrictions, okay? They restrict the graph that we're looking at. When we're doing a real world problem, there are restrictions on many of the things that you can do, okay? If you're producing or manufacturing things, a lot of times there are restrictions on what you can do, time, resources, okay? So that's where these constraints come in. The quantity you're trying to maximize or minimize is modeled with what's called an objective function. Often this quantity is cost or profit. Suppose the objective function is C, capital C, equals 2x plus y. Well, graphs of the objective function for various values of C are parallel lines. So this objective function has three variables in it. That objective function we're going to use it though to allow us to determine different costs for different combinations of x and y, whatever those variables represent. Okay, so the graphs of the equations y equals 2x plus y and 17 equals 2x plus y intersect the feasible region at 2, 3, and 7, 3. These vertices of the feasible represent the least and the greatest values for the objective function, right? So these different objective functions, depending on the c value, are going to be parallel lines, that we could translate across this graph, and they're going to intersect different parts of the of our feasible region. The ones that we're going to pay special attention to are the corners, okay, or the vertices of our feasible region. Those are the ones that we're going to use, okay? So we have this property here. It's called the vertex principle of linear programming. If there is a maximum or minimum value of the linear objective function, it occurs at one or more vertices of the feasible region. So based on this, we aren't going to concern ourselves with what's going on in here, okay? We're only going to look at the vertices of our feasible region. We're not even going to look on the boundary. We're going to look at the vertex points. Those ordered pairs are the pairs that we're going to use when we examine our objective function. So here's an example. All right, so it's a multiple choice problem. Here are our four possible answers. What point in the feasible region maximizes P for the objective function P equals 2x plus y? So here is our objective function, okay? Our objective function, we don't graph it, all right? We just use it. So after we take our constraints, graph the constraints, find the vertex points of the feasible region, then we use the objective function. So the objective function, we're just going to hold off on that for a little bit, okay? So let's take our constraints and let's graph them. So we have 4 inequalities that we have to graph. And you can see here, these two, x greater than or equal to 0, y greater than or equal to 0. Most of the time, I don't want to say all the time, but a lot of the time, those two constraints are going to be in there, okay? Now, we may have some other positive values here on our constraints on x and y, but again, think about it. X greater than or equal to 0, y greater than or equal to 0. Those two constraints tell us that x and y cannot be negative. They have to be 0 or positive. So many, many, many times those constraints will be in there. And then we have these other two constraints that are relationships between x and y. So here we graph our inequalities. So this first graph has all of our inequalities on it with all the shading and everything going on. This second graph is just a graph that illustrates our feasible region, okay? So this red line, this is our x plus 2y less than or equal to 5. And the shading is below. Our blue line was x minus y less than or equal to 2. And we shaded above that line. X-axis, okay, the x-axis here, which is y greater than or equal to 0, we're above that line. The y-axis, which is x greater than or equal to 0, we're to the right of that line. So we have our feasible region in here, okay? And we have our vertex points here, 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 and here. So those 4 points, those 4 ordered pairs, are the coordinates of each vertex of our feasible region. So here they are down here. Okay, point Q is the origin, R is 0, 2.5, S is 3, 1, T is 2, 0. The last step in this is where is P, and a lot of times capital P represents profit, but we didn't have any context in this problem, so we'll just call it P. We want to evaluate capital P at each vertex. So capital P, when x and y are both 0, has a value of 0. Capital P, when x is 0 and y is 2.5, has a value of 2.5. P, our objective function, when x is 3 and y is 1, has a value of 7. And P function, when x is 2 and y is 0, has a value of 4. So when we examine those 4 values, since we are told back in the problem that we want to maximize P, we're looking for the greatest value, and that's this one. Okay? So when x is 3 and y is 1, we get a maximum value of 7. So if we go back up to our choices, this was our correct response. Okay? So that's called maximization. Right? And you know, if the only thing about that problem that was different said minimize, then we would be talking about this value right here. But we were asked to maximize, so our maximum value is 7. Right? So we could be asked, what is the maximum, or what point produces the maximum? If this problem had context, then we might be asked, if these variables had meaning, we would say, well, we might be asked what combination of those 2 variables produces the maximum value. So we just have to make sure that we're addressing the question. This one was a multiple choice, so it's not as difficult. All right, so here is a problem, another application of linear programming, and as you can see here, these problems are fairly involved because what we're going to be given is we're only going to be given the information. In problems like these, we're not even going to be given the inequalities, so we're going to have to generate those ourselves and then use them. So here's our problem. We're screen printing t-shirts and sweatshirts to sell at the Polk County Blues Festival, and we're working with the following constraints. You have at most 20 hours to make the shirts. So there's an example of a constraint when you're running a business. You want to spend no more than $600 on supplies, so another constraint. You want to have at least 50 items to sell. Okay, so those are our constraints. How many t-shirts and how many sweatshirts should you make to maximize your profit? How much is the maximum profit? So over here in this graphic, we are told one color t-shirt takes 10 minutes to make, supplies cost $4, and we make a $6 profit. Over here, we're told that a 3-color sweatshirt takes 30 minutes to make, supplies cost $20, and the profit is $20. So what they recommend is we recommend to organize the information in a table because there's a lot of information here, okay? So we know that we have some variables here. We have minutes, we have number of shirts that we're making, we have the cost that it is to make those, and then we have profit, okay? And anytime we're running a business, we want to maximize the profit. So in this case, the profit function, when we write it, that is the function that we're trying to maximize. So these other constraints Those are our inequalities. Okay? So our minutes for a t-shirt is 10x, 10 minutes per t-shirt. Our sweatshirts is our variable y, 30 minutes per sweatshirt, so 30y. That time, 1200, right? That's our maximum amount of minutes. Okay, these are in minutes, so we got to convert our 20 hours to minutes, so that's where the 1200 comes from. All right, we know that when we go to this festival, we want to sell at least 50 shirts, sweatshirts, combination. So we want x plus y to be greater than or equal to 50. All right, our cost, what do we want to do with cost? We always want to minimize cost, so we want the cost to be at most $600. So $4 it costs us per t-shirt, so 4x plus 20y, because it's $20 per sweatshirt. We want that combination 4x plus 20y to be less than or equal to 600. So here you can see our constraints. Okay, so these three inequalities here come from this information in the table. And again, there's a lot of information, so we just have to break it down. Okay, minutes, the number of shirts we're making, all right, those are our variables. Okay, and then we have our two constraints here that x has to be greater than or equal to 0 and y has to be greater than or equal to 0, right? Because we can't make a negative amount of t-shirts, we can't make a negative amount of sweatshirts. So they both have to be greater than or equal to 0. So once we have this system set up, our constraints, and we also talk about the profit function, you know, we're told back here in this graphic, $6 profit on t-shirts, $20 profit on sweatshirts, so $6 per t-shirt, $20 per sweatshirt, 6x plus 20y, that's going to equal our profit function, right? So if we were to graph the constraints, when we do that, we get our feasible region. So here's the graph, all right? Now again, we have lots of possible combinations here that we could examine, but we're only going to examine the vertices, all right? So find each coordinate, or find the coordinates of each vertex, right? Now, we've got to use some different techniques here to find these vertices. When we have two lines, we might have to solve a system. So, for instance, this line coming down here, and then this line coming through here, we have to use our techniques of solving systems of equations to find this intersection point. We can do it algebraically, or we can do it graphically if we have some technology. Same thing here, this vertex point up here, we're going to need to use either algebraic techniques or technological techniques to find these intersections. All right, down here we don't need to do that as much because we're on the x-axis. What do we know about the x-axis? We know y is 0. So we can substitute 0 in for y and get these x values. But these two up here, we're going to have to work a little bit for, okay? So after we get those values, we get coordinates of A, point A down here is 50, 0, point B is 25, 25, point C is 75, 15, and point D is 120, 0. Okay, and remember, X represents the number of t-shirts and Y represents the number of sweatshirts. So there's some work involved here in getting these vertex points. After we get the vertex points, though, it's just a matter of evaluating our profit function. So when we evaluate P for these different values, we get these profit values. And we want to maximize profit. So here is our maximum profit, $750. We can get $750 of profit from this festival if we sell 75 t-shirts and 15 sweatshirts, okay? That's our maximum profit. That's the most that we can make, right? And sometimes what businesses will do is they will do this analysis and they will look at this and they will say, okay, is it worth our time to go to this festival and try to sell these shirts? And so they will have a decision to make. If we know that the most that we can possibly make is $750, is it worth our time or not? Okay? And, you know, that leads into a whole nother, subject. But those are the types of decisions that businesses make using this information, okay? Linear programming is a very involved process of solving real-world type of problems, okay? It uses our knowledge of linear systems, of equations and inequalities. So we have a bunch of different things that we need to keep in mind. We need to be able to write equations and write inequalities. We need to know how to solve them. and then obviously use all that information that we can generate to solve the problem and the task at hand. So we can do it. It's involved, but we can definitely do this. So hang in there, and I will see you guys next time.